It's another night of the Perseids. We're going to try to watch for them. I got the camera in a position inside the dome where it will be out of the weather just a little bit. So we'll see what happens. Yes, it is cloudy, as you can see, but you know what? The Perseids can be very bright, and you will see them streak through light clouds like this. And they're actually kind of cool to see that. So we're going to watch for them and see what we get. I also have the ability to change some of the settings in the camera. We can change some of the look. This is the normal look, but we can actually go to high contrast views like this, or a variety of other types of views. We can focus on the red part of the sensor. We can focus on different areas. I particularly like this setting right now because it's sort of a contrast with the full color palette. So this is a little better, and we'll see the colors of the meteors better here. So we'll see what happens, you know. I will be stepping away now and then. Since I'm not controlling a telescope, I've kind of tasked myself with doing a few other things around here. So that will be no big deal. This little haze you see on the right here, on the left side rather, and a little bit on the right, that's the clear dew shield that I put over the camera. We only want to see what's in here anyway. And that little edge right up there, that's the edge of the dome peeking in. Just a tad. No worries, David. I'm glad you came along. Thanks for coming by. This is the last night that the Perseids can be streamed, because tomorrow night here in New England, that is where we are going to be seeing some heavy weather. And then the following day I'm off to Norway, so I have to take care of all that. And Bill New York Skywatcher is also streaming at the same time, and I know that he's excited about it. In fact, he's going to be taking me to the airport, actually, on Wednesday evening. So that'll be kind of cool. Very nice of him to do that. He wouldn't hear of it any other way, which is really nice. So, how are you all tonight? You doing good? I know that the skies are not really terribly conducive to seeing the Perseids, but we work at it, don't we? We do our best. And if it wasn't a meteor shower, I actually wouldn't even have the dome open. In fact, the dome is open, and I'm aiming a regular camera out of it, as I said. So we're doing this just because it's the Perseids. It's magnetic resonance imaging, Ronald, MRI, and I've had a few, and they're just noisy and annoying. You have to sit inside a little cage that your head is held in, so you don't move too much if you're doing your head. If you're doing other parts of your body, then you still have to sit still. Is this for your spine? Is this for your head? What's it for? You know, kind of a thing. That will dictate what they do with you in the MRI. But either way, you can't move because the imaging needs to be clear and precise. And what it does is it appeals to the magnetic nature of your atoms in your body and can build an image from that. And it's actually very useful. And it's not radiation, by the way. It's not like a CAT scan. A CAT scan is radiation. MRIs are not. Actually, if you want to think of it this way, an MRI is like being exposed to a very, very high magnetic field, And a magnetic field is, magnetic field is something that would, for instance, in the case of a very, very powerful neutron star, like we talked about on a previous show, the magnetar, those magnetic fields are so powerful they could rip your body to pieces. The MRI is hundreds and literally like a billion or more times less intense, several times so, than a magnetar. So we're talking about low levels of magnetic resonance versus what the magnetar does. But boy, the high magnetic field of that magnetar that generates fast radio bursts from billions of light years away, those magnetars are really, really high, powerful, very high power bursts, bursters. And because the magnetic field is so high, we as humans couldn't get anywhere near them without being literally ripped to shreds by the magnetic field. It would disassemble our atoms. No time. So yes, it's the Perseid meteor peak, such as it is. How exciting! But we do have some clear skies, or some clear skies here. If we see one, it's going to you'll see it streak, and it'll actually show through the clouds. I've said this before. We actually I had a meteor streak through. When I was in graduate school, I had a meteor streak through the view, actually through my vision, from left to right, and it was actually a driving rainstorm. And through the rain, I could see this greenish yellow meteor just above the clouds. It showed through those clouds. So sometimes you get these amazing gems, you know. Hey, Most Intelligent is here. How you doing? Bobby, you're here. Good to see you. And of course I said hi to Ronald and Dave Schmidt. And Evan is here lurking in the background as well. At least that's all that I see in the chat. I think there might be more out here lurking and watching. Let's go see, shall we? Who all is here? There's a few more of you sitting out there just watching. So, yep. Oh, so you pulled something, Ronald. Okay, gotcha. Oh, sure. I will, when I get there, I will certainly, I don't know at what point I will see Ket when I get to Norway, but we will certainly be looking to talk to each other, because we're going to be doing talks over there together in the same talk speaking tour, so it'd be nice. Hello, Francis Palmer. How you doing? Well, the color in the meteor tail is actually indicative of the elements that make up the meteor, as you suspect. And so sometimes the colors that we see are due to the iron or nickel that is burning away, and it's basically doing an atmospheric flame test. Just like perhaps when you might have been in high school, you actually held a particular element over a flame and you identified it based on the color. Well, in the case of meteors, we also do that, and meteors have specific colors as well. I'm going to dig for something to maybe help explain that just a little better, because sometimes a picture's worth 1,000 words, and I actually put together a picture, and I might be able to find it. Otherwise, I'll have to look for it online. Hang on, I'll just look for it right now. Okay. this, I think I've got one here that might help. Hang on one second. Okay, let me drop this down to here. And let me see if I can go bring it up. And I might have to interrupt some things a little bit, but it'll be all right. When you're talking about nitrogen or oxygen, either way, nitrogen and oxygen in a meteor would make it glow red, actually. And we don't really see red that often. But let me grab this here for you. Okay, I'm gonna go to a different screen for a second just to bring this up, and there we go. So now you can see the colors of a meteor. All right, we have the reddish colors will be nitrogen / oxygen, and yellow is typical. These are the Perseids, are usually this bright yellow. Okay, and the calcium will be purple. Sodium will look a little like sodium vapor lamps. Magnesium has a bluish tinge to it, which we've seen. All right, and you also see green, so you see a mixture of sodium, magnesium, and others, and iron. And usually when we put these together, you will see a greenish hue as well. But I just thought that is probably one that's probably a image that will help you. Now let me see if I can take this image and make it something that we can store for usage later here. So we'll keep looking here. I'm gonna try and pop this image in here. 1 second. Let me grab it here. Yes, this will be all right. This should be able to help us. 1 second. All right. That's the one we want. Okay, and so we have it here on the main screen, so we'll actually have access to it. It's a little small, but you can still see that, I think, right? You can tell me if you can still see that. I hope you can. Hey, Gas Mask, how you doing? Astro Live, nice to see you. Yeah, strontium burned very red. You're absolutely right. But it's not the only thing that glows red. See, that's the problem. We find it in chemistry. We'll have this overlap like you can't imagine. So here we go. So now what you got, you have the meteor colors here. So if we see any over here, we'll actually be able to see the colors. I'm going to guess that most of them are going to be yellow. All right. And I think that it's actually... oops, that was not what I wanted to see. Little mistaken thing there. That's better. I think we're going to see yellow most of the time tonight. But you never know. You never know. So, we're running with a little higher contrast, but I said before we can change things around. If we want to go to like high contrast black and white, we can actually do that. And this one, although it's black and white, the problem with that is that it will, unfortunately, it'll remove the color from what we see. I prefer to go into this realm, which is higher contrast, but it's, color at least. Nice, So I'm not sure what we'll see. But like I said, look for the bright flashes from behind the clouds too, because of course they are above the clouds. And you got your meteor color reference over here to see what to expect on the screen. As I said before, this shadow here is part of my curved dew shield. I made a clear dew shield earlier, and this little snip over here, that's actually part of the dome, because I put the camera on a tripod inside the dome so that we can watch it directly and not worry about dew as much on the lens. And the dew shield is just a shield around the lens. It doesn't go over the lens. Interesting, Ronald. You saw that from the postage stamp that you live on? Out in Jeffers? Yeah, Swift Tuttle. Okay. I'm doing 92 things at once here, guys, so you know, that's how it works. Okay, let's see here. Excuse me. Alrighty, so very exciting. If you guys have any questions, feel free to offer them up. Happy to help you out. Hey, Missy Bennett, I didn't see you show up. Thanks for coming. Good to see you here. Mario, there you are. Nice to see you too. You know, I said hello to Gas Mask and Astro Live. Very nice to see you guys come out tonight. It's sort of cloudy here, and I don't know. I don't like clouds. None of us do we? But sometimes they present some interesting opportunities. We can watch the clouds and see the meteors streak behind them, and they illuminate the clouds sometimes in most spectacular ways. So it'd be kind of neat to see what we see. Indeed, indeed. All right, let me go check something out here. Hey Rock, how's it going? Apostasia Realista. Hey. Yeah, hey Marco. Yeah, you know, it's pretty it's pretty unfortunate with the clouds, but you know what? At least we have some breaks, as you can see here. We can get a little bit in between. Every now and then you'll see a star that is visible through there. And you can see the direction they're moving. Obviously, this, let's just so you know, this direction over here, we're facing, this is about north right about here. Okay, so this is northeast, and they're coming from the northwest and west-northwest and sort of going toward the east. And of course, that's the problem. Genghis, how you doing? Well, it is what it is, you know, but it's okay. We're doing okay. Doing okay. I'll tell you this. If also, for those just joining, if you notice on the screen here, I put up the meteor colors so you can see. If we see meteors, you'll see their colors, and you can refer to this chart, which tells you what you're looking at. Okay, so the first one, for instance, is nitrogen, oxygen. Primarily, if there's nitrogen and oxygen compounds in the meteor. Next one's iron. Next one's calcium. After that, sodium. Kind of looks like a sodium vapor lamp, actually. And then we have the magnesium. And you'll see green as well. So there are meteors that come streaking in that give off a greenish hue, and usually that's a combination of some of the things you see here. So this is the predominant ones. There's more. There's different ones, of course. But this is what we see pretty much. Hey, Tim F. Good to see you. You know, we'll be here for a while. We're gonna try and wait it out for the breaks in the clouds. You know, Kenny, we want to just catch a break, don't we? Yeah, came for the stars, stayed for the jazz. That's kind of funny. Good one. Yeah, well, these clouds actually, I'm running, let me show you in a high contrast mode with the camera. If we go to high contrast, you can see that these bright spots are where the clouds are. These darker areas are where there's lighter clouds and some breaks actually in the clouds. So popping into high contrast is very helpful sometimes to actually see this. And right now I'm using something that will exaggerate the colors just a bit so we can actually see the fainter meteors if they come through. And again, we have the meteor reference over here that you can see, which tells you what colors to expect. When you see a color, you can figure out what's in it, basically, based on the flame. Yeah, I know, Rock. Bill has some clouds, and that's just the way it works, you know. I can't always predict what we're gonna get, unfortunately. It's actually not, you know, it's still early anyway. It's only 11:25. I've got a couple more batteries that we'll be able to use. Francis, yeah, the meteors that explode are really spectacular, and meteors that come in that are, well, the size of grains of sand, typically, they burn up and then they're gone. They're very, very fast, and you can see them from 150 miles away as they burn up, because they're translating all that energy of motion, we call kinetic energy. They're translating it to heat, and that really makes a massive amount of energy release when you have even a tiny grain of sand. But when something larger, like a pebble, comes in, or something the size of a hard ball, baseball, comes in, holy cow, that changes everything. Now you'll see not only the sky light up, you'll see your shadow by it. You'll see a smoke train behind it as it burns up. Because remember, it's entering the atmosphere at several thousand kilometers per second sometimes, and that's actually pretty fast. And it gets to the atmosphere in no time, and then it starts moving in. And even though it's only hitting a few atoms of a few molecules of the atmosphere, where they come in at around 100 miles to 90 miles or so, it's gone from hitting nothing to hitting these atmospheric molecules in a split second. And that heats the meteor up so intensely that, of course, it begins to glow, and then it begins to melt, and then it begins to do what's called ablate. It begins to break off pieces of itself. Sometimes that the aerodynamic pressure on it is so high that the meteor will basically be like hitting a wall, and you'll see it just go boom. It'll break apart, but you won't hear that sound right away. But sometimes, a few minutes later, you will. And I mentioned yesterday, I was in a field watching a meteor. It streaked all the way across the sky, and then it broke apart into like 3 or 4 distinct red-hot objects that I could see before they faded away. And a few minutes later, I heard with an echo. It was just amazing. And of course, that was the meteor breaking up, and the sound. The other thing, and I mentioned this yesterday too, which I haven't done yet, is I'm going to add a meteor radio to the dome, so that during any streams, we will be able to listen for the sounds of meteors coming into the atmosphere. Give you an example. When a meteor comes into the atmosphere, it gives off light. But light is also, visible light is at one end of the spectrum, and then at the other end of the, farther into the red, is the radio spectrum. And so sometimes a meteor is not restricted from giving off other types of light. And since radio waves are light, you will definitely see. You'll definitely see the meteor in the visible spectrum, and then you'll hear the meteor in the radio spectrum because it leaves a little burst of meteor noise, so to speak. I call it the meteor music, and it's like like a little whistle, and they're really kind of fun to listen to. On a heavy-duty meteor storm, it gets really annoying really fast, but let me tell you, it's really kind of cool. You know. So we're just waiting. I'm just trying to get a feel for whether we're gonna see anything through these high clouds or not. Yeah, well, we still have a chance. The Chelyabinsk meteor was actually an amazing meteor in Russia. It was, I'm trying to remember how big it was. I think they estimated maybe 16 feet or so. And when it entered, it actually hit the atmosphere and began burning up right away. And when it hit that wall I talked about earlier, it exploded, just as several of you mentioned in the chat. And it's hey Keith, and when it exploded, it completely disintegrated, and it created a shock wave, which came down and struck on the ground in various places, and it blew out security doors. It knocked people over. It hurt a lot of people, and that was just a tiny meteor. Can you imagine if an asteroid a quarter mile across came in? I calculated, like I mentioned last night, I calculated what Oumuamua would have done had it hit us. And Oumuamua, we don't really understand really just how it really looks. We know it was about 10 times longer than it was wide. So it's sort of a spindly asteroid. That's how we know it was not from here. And yes, Oumuamua would have struck with the force of about a megaton. A megaton. So it's actually not something to quibble with. I can tell you that. I want to answer Francis' question, and to do that, I'll be right back. I'm just gonna get up for a second. Francis, you asked, I think you're addressing it to me, do I have any meteors? And the answer is I do. And I'll show it to you. Here it is. See that shape? It definitely shows the ablated shape. You know what? I'm going to turn the lights on here. Let me get series to bring my lights up a little higher. So we'll go up to this, and now you can actually see this meteor up close and personal. All right. So this is what a meteor looks like when it finally reaches the ground. This one is solid iron, so it's actually pretty heavy and not easy to hold like this. Okay, and it has all kinds of really interesting. It has all kinds of really interesting, convolutions and little craters in it, and looks cool. Like, look at that. I mean, that's really neat looking, huh? And so this meteor, being all iron, is, like I said, very heavy. Weighs about 1,000 grams, and they measure the value of meteors by their mass, their weight. And so this one weighs at about 1,000 grams. So you can figure out by looking online what's the going rate for iron meteorites these days, and you'll see, it's going for about however much an ounce or whatever, and then you figure out how many ounces you have, and in boom, or grams. They measure it in grams, and then you can actually sell your meteorites. This one, this was part of an Argentinian fall, one that came from Argentina, and it's actually, like I said, it's really heavy. Hey, weird guy, if I was to slice this, you would see some beautiful mineralization inside and crystallization in the meteor that could only occur in space. And some people slice pieces off of these, and they actually will turn around and make watch faces out of them, and then make a watch with them or whatever. And it's really quite interesting. There's an awful lot of things that people can do with meteors. Me, I'm not a baubles type guy that would do that. As you can see, I don't even wear a watch because I don't need one. But I prefer to just leave the meteor untouched in its natural state. And this actually, when it came to me, it was actually beautifully silver, believe it or not. And I ended up just sort of leaving it in a bubble wrap bag. And hey Katie, that was the mistake. The bubble wrap bag actually allowed the iron to oxidize on the surface and basically rust. So I can get rid of the rust. That's not a problem. Getting rid of the rust is actually easy, but it is a really neat rock, because you can actually see how the atmosphere acted on it. And that's what we're watching for today, are guys like this. If this entered the Earth's atmosphere like this, okay, this was from a much larger object when it came in, but if this entered the Earth's atmosphere like this, then this would have made a very, very bright streak across the sky, probably with smoke. And so you would actually see this thing very brightly through any clouds there are, without any doubt whatsoever. So I think that's pretty cool. I am losing heart tonight in looking at the weather. I realize, I'm looking back and forth with Bill New York Skywatcher, and in the background we've talked, and I can see that we're looking at clouds that are only going to get thicker. But we hold out all hope that we can see one of these bright ones flash through, because what's going to happen as soon as we stop streaming. That's when that amazing meteor comes piling right through the scene that we haven't seen in like 100 years. The 100-year fascinating meteor will come through. But until then, we can sit here and just play with the lights and make them do some cool things. I prefer I like my my lights. They're programmed lights, obviously. They're Wi-Fi lights. So we end up doing some cool things. You know. I was in Los Angeles last week for 4 of the 5 days, and I was filming for a new Discovery Channel show, which premiered that. Actually, the first episode premiered that very night I was filming. That night is when the first episode appeared, and I was actually doing the season closer episode, which is kind of cool. But then the next day I did a Travel Channel show, and we were talking about astronomy. We were talking about fast radio bursts. We were talking about other elements of astronomy that are very fascinating. So it's actually going to be a good show. I enjoy being able to participate in astronomy shows because that's my science, you know. But it's all good, you know. Oh, Rock, were you talking about the meteor? 1,000 grams. Yeah, that's actually it's a good size. Don't throw it in a lake; it'll just sink into the mud. Hey, Ghost. Hey, Cindy. Nice to see you guys here. Yeah, you know, I think. Hey, BlackRock. Good to see you. I mean, everybody, you know, people don't go back and forth between the streams. It seems like our sky is starting to get as bad as Bill's has become. So I'm not really too excited about tonight. That's too bad. You know what? It happens. It happens from time to time. You know, it happens from time to time. But somewhere there's a stream where there is a clear sky and they can simply watch for meteors tonight. I'm reading your comment, KDQ. In Portland, there's a place called the Fossil Cartel. They used to have, they claimed it was a meteor that was nearly 4 feet tall. Don't think it's there any longer. Well, it may not be untrue. I mean, there are meteors that have hit that large. I gotta tell you a little story. When I was getting my astronomy degree, I actually my whole career was in old musty astronomy buildings with big domes on them that actually had libraries with floors that were wooden and that creaked. Old books and stuff we had to research, and then online and do the internet searches. True classic astronomy, really amazing to do it that way. Everything being manual. You open up these big charts and lay them out on a massive table and just start going through them in order to study some of the stellar positions, because you had to figure out where the stars were so that you could then map out what are called program stars for your stellar brightness studies or whatever you were going to do. And in the library at this university, there was a piece of the meteorite that carved out that giant hole in Arizona. The Behringer meteorite, now a famous world attraction called Meteor Crater, Arizona, west of Winslow and east of Flagstaff. Well, that meteor was around 28 inches long, about 30 inches tall, and about 22 inches wide. Solid iron. It weighed almost 500 pounds. And we, the four of us, there were four of us there, we saw that meteor one day. It was about 1 a.m. We were really tired, and we were just feeling a little punchy because we were working on something, spectral analysis or something. So we didn't even talk. We didn't say it. All we did was walk over to the meteor. I looked at Ron looked at me, Ron and I looked at the other two, and we just kind of looked at the meteor and said, well, let's bring it in. And we all knew exactly what we were going to do. We picked the meteor up together, and we walked with it very slowly into the director's office course, he was gone because it was 1 in the morning. And we put it on his old wooden chair that he sat in every day. And of course, I was working all night in the dome that night, and so I was there when he came in the morning. I was just about to leave to go and go get some sleep. And he comes in, and I'm in the dome now, and I hear him bellowing, "Who the beep put this beep meteor on my beep chair?" And beep. I mean, if there would be $1 million worth of beeps if you got a buck a beep. It was really funny. So we Ron wasn't there yet. I was still there, and there was a couple other guys in the office. And we kind of looked at each other and said, "Oh, maybe we better kind of go in and own up to that, maybe." And we saw his face. The guy had a beet red face, and he was really stewing. It's the thing you do. And we said, "Don't worry, we'll get this off the chair for you." And we must have looked too efficient, because we took it off his chair, moved it back into the library with no problem. And he said, "Thank you," he goes, "but I have this sneaky feeling that you're the guys that put it there." And we kind of laughed. And we said, "We didn't know it was going to upset you, sorry." And he basically almost cracked a smile. But he said, "Well, I'm busy, so it didn't strike me as funny today." I went, "All right, sorry about that." And we went on, and it was very, very funny. But that's the same guy that yelled at me when I said that I believe it's a populated universe, and I do. Because I was always going head-to-head with people that were suggesting that maybe we were alone in the universe, and I was always saying, well, no, I mean, it's pretty clear that there's more to the universe than just us. Our world is one of many. That was my conviction. And I was talking to the same guy, the director of the observatory at that point. And I said to him, "Hey, I don't know. I mean, I think it's a populated universe because of the fact that we have a lot of life on this planet, carbon-based life." And I'll talk to you about that too. I mean, this is something I talked about on SkyTour Radio. It's something I lecture a lot about around the world, and it's important because it really opens your eyes. When we think about life on this planet, every life form on this planet has one thing in common, and I'll bet you without even mentioning it, you'd get it. I don't have to mention it. Okay, the thing that we all have in common is our DNA, right? And DNA is based on the carbon atom, essentially. And the carbon atom is part of a happy little group of atoms that tend to make up most, if not all, of life. And we have a phrase for that. We call it CHOMPS. CHON, as in November, NPS. CHOMPS. That's carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. CHOMPS. And so CHOMPS makes up life here on Earth. And the materials to bring this life here, and I don't know what that weird light is over there. There was something strobing over there. I think it could have been a lens flare. Anyway, from passing light. So meteors brought carbon atoms here, and oxygen and water. Asteroids brought a lot of water, actually, as it turns out. And then the rest of the atoms were brought here by comets and meteor impacts, collisions with other bodies, of course. And then our Earth also made these materials. That's what's really cool. And we found, for instance, that if the Earth, the primordial atmosphere, the stuff that makes up what the Earth's original atmosphere was placed in a flask all by itself, and you had water in there too, and if it was bombarded with lightning, in other words, a spark electrode, a little spark gap, do that for a week, and you'll see that there's a little coating along the glass at the end of the week. You look at what that coating is, and it's amino acids, the building blocks of life. So, amino acids made by the Earth, amino acids brought here by comets and meteors and asteroids. So the building blocks of life, carbon-based, brought here by all these many things. So it made me feel, and this is what I pushed with my director in the observatory. I was telling him this. I said, it seems to me that the universe is sort of predestined to delivering these materials to a planet that's in formation, especially if it's in a place around its star where it's not too hot, not too cold, correct? And he's nodding, yeah, maybe. And of course he had to throw in, well, we're not sure there's any other planets, because at that time we weren't. It was 1983. And I said to him, so also couple that with every life form on this planet of any substantial number of cells, multicellular, they're all symmetric. They all show symmetry of some kind. A lot of creatures are bilaterally symmetric. They're symmetric across their centers, right? A lot of creatures are radially symmetric, all right? Plants and flowers, radial symmetry. And then we have, for instance, when we look at the starfish, for instance, I mentioned this. Starfish, when they're born, when they're larvae. Now we know starfish have 5 arms, right? Starfish have 5 arms, yeah. Starfish are born with 5 arms, right? They're born, they end up with 5 arms and they get bigger. But before they get bigger, before they mature, they're larvae like other creatures. They're small. So, they're the adolescents. At that point in their lives, they're bilaterally symmetric, just like we are. And as they get older, they show the pentamerism traits, that is the 5-sided traits. That's something that is amazing, just in and of itself, because it shows that it reaches from one form of symmetry to another. So life goes from one form of symmetry to another. That's key, because it shows that symmetry is something that's very important in the universe scheme of things. So that said, I said that and said, look, in that regard, I think that when we find creatures from another world, I imagine they're going to be symmetric about their centers. I imagine they may, if they reach intelligence, I imagine they may be able to show us. Gingus, we got 2 butt cheeks. Very well said. And guess what? That is indeed a product of our symmetry, our bilateral symmetry, symmetric across the center. And I said, with this kind of symmetry in the universe, and carbon being sort of predisposed to being delivered to the planets, I'm imagining that carbon-based life is probably the norm, not the exception. And his response was, he put his hand on his chin. He had a scruffy beard, and he's sort of stroking his chin a little bit. And he goes, he says, well, you know what I want you to do? And I'm thinking, okay, great. He wants me to do some research on it. He says, Mr. D'Antonio, I'd like you to get back in the observatory and work on your research project and leave Captain Kirk to us. And he spun on his heels, proud of himself for a statement, and walked into his office. So I was like, oh, yeah. That was in 1983. Now, let's jump ahead 4 years and go to 1987. In 1987, I had already got my degree, and I was out working in astronomy. And I was here in Connecticut, actually. And I saw that the first exoplanet had been confirmed and officially discussed. And so I went back into his office, and I hadn't seen him for a couple of years. So I waved at him, and he was on the phone. He waves with a smile. And I said to him, I looked at him actually, and I have this look on my face like I have a gotcha moment coming, right? And he looks over at me, and he covers the phone for a second, and he goes, "It was only one planet." And I said, "Just the beginning, just the beginning." And of course, we know now that, of course, that it was, and that certainly wasn't any miraculous prediction of mine. I just had a sense that the universe has a lot waiting for us out there. There's a lot in store. There's a lot of planets around other stars. We now know that there are more planets around stars than ever thought. In fact, there's more planets in the universe than there are stars in the universe. Let that sink in. More planets than stars. Hey, Papa Tom. Welcome. So, you know, the fact is, oh, you know, Katie, did you see that too? I actually thought I saw a streak through the clouds as well. It was, let me give you an idea. Was it around here? Tell me if it was around there, Katie. Maybe a little higher. Kind of in this area. Because I saw something there and I wasn't sure if that's what I was looking at. Well, you won't miss anything. Hey, Papa Tom. Yeah, so as you guys can imagine, you know, being in astronomy in this day and age is really just amazing. So if you think about it, okay, you can actually, by the way, see a star right there. There's one star poking out of the clouds right there. So you see, it's thin enough. We'll be able to see something. But this is where we need to be looking down here. That's probably one of the stars of Cassiopeia, by the way. So when we look at astronomy, you have to understand that every single thing we've learned in astronomy, almost every single thing, I have to, besides thinking about the missions to the moon and the asteroids, the lunar missions, and the asteroidal missions, the only way we've learned is by looking at the light, the electromagnetic radiation coming from objects to learn about them. That's all we got. We can't touch stars. We can't touch neutron stars. Thank heavens. We can't check out black holes up close and personal. We can't make a black hole to check it out in a lab. We can't play with neutron stars. We can't play with pulsars. All these things are massive scales compared to us. And we are stuck just looking at we're stuck just looking at the electromagnetic radiation, the light coming from space and going through our atmosphere. So we also have to take off the effects of the atmosphere on everything we observe from the Earth. And that's another thing we've done a lot of. You know, when I observe stars close to, I don't know, let me just use the cursor here. Okay, so this is about this distance right here. This is about right here is around 41 degrees up. Okay, and if I looked at a star that was up here, and I looked at a star that was down here, well, the difference between this star and this star, they could be the same brightness. Let's say a magnitude 6 star. Maybe they're both magnitude 6.02. Okay, that's our brightness scale, magnitude scale. If they were both magnitude 6.02, the star down here would look fainter than the star here. And the reason is because of the fact that the star here, we're seeing through less atmosphere than the star here. Remember, the stars are, of course, very, very far away. And because they're so distant, when we look at them through here, we're seeing them through an angle out of our atmosphere. When we look at it here, we're looking all across the atmosphere for hundreds of miles away, in addition to our view, and as opposed to this star. And we're seeing it through more air. And air tends to do something called extinct the light. It tends to dim the light, attenuate, reduce the amount getting to us. And so we have to calculate the extinction at all the angles, from up top all the way down to the ground, to our low levels. And so we try to not look at stars, for instance, that are, say, below a certain angle above the horizon. And I forget what number we used. Maybe it was 35 degrees. or so. So maybe about like here, only here and above. So that meant that whenever you did a study in the observatory, you would always tend to make sure that you got telescope time such that the stars were in that position. Because as we look over the course of the night, last night, Cassiopeia was down here, then it was up here, then it was up here. So it wasn't always visible, and it wasn't always in a good position to observe. But we would have to pick when we could observe it, and do that. So it's kind of interesting. I just think it's really fascinating, And we've learned a lot with astronomy lately. We've been able to do some really interesting things. One thing that came across that's very interesting, that's coming out now, is that it looks like we were wrong about something called the Hubble constant. Now, the Hubble constant doesn't have anything to do with the Hubble telescope, but it has everything to do with who the Hubble's named for. Edwin Hubble in 1929, he discovered that galaxies, as far as we could see, were racing away from us and each other. Now, that was an interesting find, because galaxies that are moving away from us and each other means that something is making them all move away from each other. That's really odd, and we didn't know what that was, neither did Edwin Hubble. But he came up with the fact that the universe is expanding, but not galaxies racing away from us. Space itself is expanding. And this is something that was really perplexing, something that science couldn't really get its arms around for a long time. But we by observing how fast these galaxies were, and the term is receding from each other, we could determine the rate at which that was happening, and that rate is something we call the Hubble constant. And yes, Papa Tom, that's right. You measure the redshift. That's exactly right. The redshift was the means to discover this rate. Now, to understand what I mean by the galaxies all racing away from each other, that's kind of odd sounding. But think of it this way. If you have a balloon and you blow it up just a little, and you put all kinds of dots all over the balloon, little tiny dots everywhere, and you start blowing up the balloon again, every one of those dots is going to race away from the perspective of any one dot from each other. The balloon will get bigger, and the space between the dots will grow larger. There's no dot that's going to be closer to another dot when you're done doing that. And that's the concept of the inflationary universe, the universe that's expanding. The concept was novel, the concept was scary, the concept brought ridicule upon a lot of people, but the concept was true. And we actually have discovered that the universe is expanding, but beyond that, lately, what's happened is the Planck telescope has been looking at, back to the cosmic microwave background, and getting values for the expansion rate of the universe. We've been looking at Cepheid variables stars, which vary precisely in precisely timed patterns based on their brightness. So if you know the brightness of the star, the pattern of the change of the brightness, because they vary in brightness, then you know how bright they are intrinsically, and that gives you their distance. And I can teach you all that at some point if you want to learn. It's called the distance modulus, if you ever look that up. All right. And when you measure the Cepheid variables in these galaxies, and you do this very accurately, and you measure it today versus back when they came up with the original Hubble constant, we discover something odd. We thought we were just going to confirm the expansion rate of the universe. We didn't. We found it wasn't right. In fact, it turns out that the universe is expanding something like almost 10% faster than we thought. Now, not only that, it's accelerating as it expands. It's going faster and faster every moment. So that becomes a big problem. What does that mean? Wow. So this expansion is what fueled the fire for the search for the new something in the universe, and I use that term precisely, the new something in the universe that's causing the universe to basically expand faster and faster every moment and accelerate outward. What it says basically is that galaxies and so forth out in space are being forced apart from each other. So it's not the galaxies that are increasing their speed. It's space that is forcing the galaxies further apart. Space itself. Now, I know that's confusing. That's exactly right, Francis. You're going exactly where I'm going. You said dark matter, dark energy, and that's exactly right. The something that's causing space to basically be pushed away from, or push objects away from each other, is something that was coined dark energy. It's called dark energy not because it's black. It's called dark energy because we don't know what it is. We do not know what it is. All right, I'll say it again. We don't know what dark energy is. And we do know that it's a repulsive force. It's pushing things away. It might be on the outside of our universe, and basically acting as an attractor to mass, causing it to accelerate outward. It could be in our universe, all throughout our universe, which we kind of think it is. It makes up 73% of the known universe. All right. And now we only know about 4 to 5% of our universe. That's all we know. That's it. So when we talk about the universe, we see it only makes up this small percentage. The mass only makes up this small percentage. The stuff we can see, stuff we call baryonic matter, matter that's made of protons and electrons and neutrons, atoms, things like that. So dark energy is a mystery. And you might say, well, where did dark matter come from? Well, when we look at things like the Big Bang, we discover that during the Big Bang, a certain amount of mass just exploded into space. And it was actually not the matter that exploded, it was space itself that blew out into a universe. Really, really hard to understand and hard to fathom. But think of it this way now. This matter that blew out into space, as that happened, okay, we ended up seeing that there was some clumping going on, and things started to, over time, clump together because it was sort of a random thing. And that clumping was nice because it helped us come into existence. And if the conditions were just slightly different, then this would be a lifeless universe. All right, but they're not. They are exactly what they are to make us who we are. Now Katie asked, what happened before the Big Bang? I wish we knew. Because the whole problem with this dark energy problem and the fact that the expansion rate of the universe has been accelerated has caused us to rethink the age of the universe, Katie. Right now, we think it was, we were saying for a long time, it's 13.8 billion years old. It might actually be only 12.5 billion years old. You might say, it's just a billion years. Actually, that's a huge amount because a lot of our cosmology, what we believe for how the universe came into existence, is based on that age of the universe. That age corresponds to a size of the universe. The universe is about 92 billion light years in diameter. We can only see out 13.8 billion years, billion light years, and that corresponds to a time where we could just see the cosmic microwave background it's a short time after the Big Bang. Now, I don't know what happened before the Big Bang. I just don't know. And Astro Live is saying, things are going to change after the James Webb goes up. You betcha it will. The James Webb is an infrared telescope, kind of like the Spitzer on steroids. It's actually a it's 21-foot diameter mirror versus the basically 3-foot mirror for the Spitzer. And the diameter of a mirror corresponds directly to how much resolution it has. So we're going to be able to see atmospheres of planets around other stars with this thing. It's really wonderful, you know. Hey, Papa Tom, I'm glad that you came by. And we're getting progressively cloudier here, so I'm kind of disappointed. But you know what? I have a bunch of good people who are hanging out and listening, and I'm happy to continue talking if they want to hear it. So the concept of the Big Bang is still there. We know that it's not a steady state universe. You know, Fred Hoyle in the early days of astronomy, you know, he had theories and other people had theories, and they were always at odds with each other because we didn't have enough data. You know, so the bottom line is that we will be we'll be on the forefront moving forward here, and we'll understand a little bit better in the coming years data that people 100 years ago could not even imagine or fathom. And I think we're doing pretty good. So right now there's TESS, the Transiting Exoplanet Survey Satellite, which is up there. TESS is an amazing instrument. David Thomas is the CEO of thank you, Genghis. Thank you very much. David Thomas is the CEO of Orbital ATK, the company that built the rocket and the satellite, the TESS satellite. And I talked to David a few times, and I talked to him on the night they launched TESS, and he said, "Oh, we're going to be launching TESS." He says, "You're going to watch?" I go, "Oh, yes." And by watch, we actually saw it launch from here. And it because we live in a round planet. Don't tell the flat earthers. Because we live on a sphere, when the satellite launched, it took 90 seconds before it came up above our horizon because of our distance. And that has to do, of course, with the sphericity of the Earth. But as I said, don't tell anybody. And then there it was. It's an unearthly color that you see in the sky as it rises up. And we watched it go until its first stage went out. Really, really cool. So we had this little in when he told us where it was going and when it was going to go up. And bam, we just looked and there it was. It was kind of cool. So we also have, and TESS is, of course, looking for planets on a whole scale manner, and our world here, we basically, we have the Kepler Space Telescope, which is kind of like a laser focusing on one star at a time, and the TESS satellite is looking at thousands of stars at a time. So it's quite a jump in capability, frankly. And so we have the TESS telescope, which is going to give us this amazing data. We have the James Webb, as Astro Live said earlier, which is going to change everything about what we think. And then we have other scientific achievements that we've recently done, which have made a world of difference in what we can do. For instance, who remembers the image of the black hole that we saw? That image of the black hole is one that is unforgettable for a number of reasons, and I'm gonna see if I can go find it just to show you. I think you remember this. Oh, I have one. Never mind. I know where it is. Okay, hold on. Pardon me. I'm gonna go grab it. I want you to see it, because I'm talking about it and I know I can show it to you. Let's see here. All right, I'm getting there. Just a minute, tease. Oh, but anyway, what I'm getting at is the black hole that we have seen represented an amazing leap in technology. All right, and this amazing leap in technology was actually kind of a trick, a little bit of a trick that allowed us to actually find and see this black hole the way we did. And I think that's really cool, and I will show you here. Here we go, and here we go, and I'll bring up this one. Okay, so now I'm gonna go take us to another screen right now, and I'm going to add another. Actually, I can do that in here. We still watch. I'll just add another one. So let's do that. It's an image you actually have not seen before, I'm sure. And I'm not kidding, because there's another one that's pretty interesting here. So it's this one. So this is the black hole that you this is the black hole image you've seen before. This is the image of the overall galaxy in which it resides. It's the supermassive black hole at the center of a galaxy called Meteor 87, and it's hey Daryl, and it's 55 million light years away. And at 55 million light years away, okay, this galaxy is, of course, we would think is too far to see anything, except it's not. We can actually see the black hole right there, and the close-up of it is right here. So we're actually seeing the black hole in the middle of this galaxy. Now, that's a concept in and of itself, which is crazy. What is a black hole? I mean, well, it's Astro Live's right. It's a Meteor 87, and it's a black hole is a collapsed star. And you're like, what? A collapsed star? What the heck? And sure, it's not something you can readily understand. But you know what? The bottom line is that a star that is large enough to collapse into a black hole is going to create something that's really quite effectively out of this world. So this object right here, this black hole that we're looking at, I want to tell you, okay, this shape that you're seeing is a case where science exactly predicted what we should see when we actually were able to image a black hole eventually. We see this brightening here. This was predicted. I'll tell you what that is. Okay, we see this overall donut shape, and we see this part here. You're actually seeing the event horizon of the black hole. Okay, this is the boundary through which, if you pass, you could never escape if you're light, okay, or anything else. So when we look at this, and yes, Astrolive, we actually have imaged M87 and the radio jet, which is here in Meteor 87. We've actually imaged this a number of times in SkyTour LiveStream, and Daryl's here. He can tell you about it. We've done it. So this shape was predicted. Now, what is this bright area here? Is this a mistake? Why are we seeing it orange? What's the light we've captured here? Well, this is just radio waves that have been converted into a color just so we could see it. And because it's out in the red end of the spectrum, it was tinted orange. It could just as easily have been tinted blue or green or purple with polka dots. It's just an arbitrary color. It doesn't mean hot, but in this case, it should be exceedingly blue because it is actually very hot, and we know in astronomy that blue things are much hotter than red things. So this bright area here is actually the accretion disk, the disk around the black hole, where the material is circling the black hole and going into the black hole and orbiting the black hole. Well, this is the material that's coming toward us. It is a little bit higher energy, so it's brighter. This is the material going away from us, so it's a little dimmer. And you might say, wait a minute, are you saying that the stuff is going around the black hole like this? I mean, how's it going? It's coming out of the page and going into the page here, out of the page and into the page. Well, effectively, yes, but now the confusion arises when I tell you that would happen from, and look this way, from any direction we look at it. They go, whoa, what? Yes, from any direction we see the black hole, whether say we're on the other side way up here, we'd see just like this. Over here, we'd see just like this. How come? It's because of the fact that the black hole has such a strong gravitational field that it's actually warping space itself. And the light rays are not being bent by gravity. That's a key point you have to understand. The light rays are not being bent by gravity. They're just following the curvature of space. So if there's a mass that bends the space curvature, that curved space, the light just follows space. Kind of like a car that's going over hilly terrain. The car follows the hilly terrain, goes up around and over the bumps and down and around. Okay. If the car was a particle of light and the hilly terrain was just the fabric of space, then you could see it better. And that's kind of what it is. Light just follows space. It doesn't know it's going in a curve. It's going in a straight line as far as it's concerned. But that straight line has been curved by a gravitational field. See? So that's kind of how this works, and it's a good way to think about it too. So when we see what we see here on the screen, we see where light is appearing from around the edges of the black hole from whichever direction we look at. But now you see it makes more sense. Go on the other side, it looks the same. Why? Because the gravitational field is bending space, and the light that's coming up from the accretion disk on the other side goes up, gets bent around toward the front from where you're looking, some portion of that light. And so it gets bent around and comes toward you. So the part that's coming toward you on the accretion disk side, the accretion disk is orbiting the black hole. Well, that part of the orbit that's coming toward you is shifted into a little higher frequency, so it's brighter. That'll come around the black holes through the gravitational field, get bent toward you, and so you'll see it. You'll see the other thing too, the same way. You'll see the other stuff going away the same way. So no matter where you look, the black hole like this is going to look like a donut. All right, and it has to do with the fact that space gets bent, and so it doesn't leave any choice for the photons of light, say on the other side of the black hole from you. When they go up off of that accretion disk, they're being bent. They're actually following the bent space, which takes them around the top of the black hole and into our visual field. So that's why this looks this way. Really, really cool stuff. And to think about it a little differently, you say, well, you think about the concept of space being bent, and it's like it confuses you because isn't space empty? Don't think of space as being empty. Think of space as being a medium like air or like water, but just different. So you can manipulate air, you can manipulate water, but you can manipulate space as well. It just needs a force like gravity to do it. And that's kind of how you think about it. Yes, actually, that's a very good question, Daryl. If you look at the image, we do know that in this particular image, the black hole is spinning kind of, this part of it is spinning toward us, and this is going away from us. So it's sort of on an angle, and this is coming out of the page and going into the page for us. But no matter where we look at it, this brightening might appear at a different location around the disk, but it's still going to be there in some capacity. And so it'll just be orbiting, say it's orbiting from bottom to top, orbiting like this comes out, this goes in, comes out, in. Okay. Well, from another direction, it's going to be bent around. And so we're seeing, that's why we see it bent like this, because we're seeing the accretion disk is sort of a broad disk from our point of view. And so the part that's being bent around is most bright here. So this is probably more related to the actual angle of the accretion disk, but we're seeing it sort of on a little bit of a shallow angle. So we're seeing it not seeing it like this if you look in the small image of me here, the hand, but we're kind of seeing it like this, sort of at an angle. So everything out here, everything out in this area out here, where it's very bright and coming toward us, that gets bent up and over the top and into our field of view and gets stretched out, so you actually see it as a little bit brighter area. Overall, it ends up being about half the accretion disk. If it's truly edge on to you, then this overall amount would probably be reduced a little bit. So you see, that's kind of how that works. It's the neatest thing, man. And so black holes typically are they kind of again, these broke all the rules. But down in the lower right hand corner you can see EHT. That means Event Horizon Telescope. And the Event Horizon Telescope is how we got this image. This is a Chandra X-ray view of it, the X-ray satellite. And then this is the EHT. Again, 55 million light years away. To actually see the round shape of a black hole is a colossally amazing achievement. But you have to understand the size of this. You ready? Okay, that's not what I wanted to show you. Let's go back to this. Okay, let's take a look at the size of this. All right, if we go back and look at the size of this black hole, all right, this distance from this side to this side, are you ready? The distance from here to here is, are you ready? 6 times the diameter of our solar system. In other words, from here to Pluto times, well, it's the radius from here to Pluto is 3 times. So that's the radius of this thing from here to here goes from here to Pluto. So from here to here is basically twice that. All right. So we're talking about 6 times the size of our solar system. All right, to get to this diameter of this black hole. That's how big this is. Now, black holes are measured by the size of their event horizon, which is this black thing we're talking about. And the black hole's event horizon is actually the object which from which, as we said, light can't escape. But you know what? The size of that event horizon is dictated by the amount of the mass that's in the black hole. So when we look at this and we see the black hole, we have to imagine and remember that inside this black hole there's enough mass to make that radius of that event horizon, this black area that we talked about right in here, okay, there's enough mass to make that thing that size, because mass determines the size of this event horizon. So you have to imagine there's a huge amount of mass in there, billions upon billions of suns in there, basically. Unbelievable, So like I said, over here, for those of you still looking for meteors, I'm hoping it's not actually sprinkling out there right now because I have the dome kind of partially open, but I have everything pulled back from the opening enough so it can't get wet. But over here we have our meteor colors, the dome ops, of course, and our black hole discussion up there. So I think that's pretty cool. Hey, Daniel Whitaker, thanks for coming along. Yeah, Daniel, that's a very good idea. That's a very good analogy. Yeah. But I have another one for you. Just imagine someone in Los Angeles holding up a quarter, and someone in Washington, D.C. being able to read the date on the quarter. Okay? That's the kind of resolution we got from the Event Horizon Telescope that delivered this black hole image right up here. All right. And the reason that we were able to get that kind of resolution actually has to do with the way this was done. And I'm going to show you another image that will actually help you with that. Okay, when we look at how the Event Horizon Telescope works, it all comes down to radio telescopes right here. These are radio telescopes. In fact, these are just some of the many radio telescopes that are used or were used to create that image. The Event Horizon Telescope was a network of radio telescopes around the world that were trained on Messier 87, this galaxy where this black hole is, and allowed to look at it for as long as they could see it while the Earth was rotating. And during that time, they were able to capture a swath all the way around the Earth, and not all the way around, but in their field of view, so about like half of the Earth, the diameter of the Earth, basically, of an element of this black hole. And other telescopes did as well. When you add them all together, basically you had a rough approximation of a telescope that was the diameter of the Earth, which is 8,000 miles. So you had an 8,000 mile telescope, and that's how we got this immense resolution from 55 million light years away. Now, that's one thing. But guess what? The Event Horizon, called the EHT, is now doing something else. The Event Horizon Telescope is being used now to examine Sagittarius A. What's that? It's the black hole at the center of our own galaxy. Ooh, ah. Now that's cool. That's cool. So that means that the Event Horizon Telescope is going to be able to view our own galaxy's black hole in a far better resolution than it did the 55 million light year distance black hole. Here we're only talking about 25,000, 30,000 light years to get to this black hole, not tens of millions of light years. So we should have a pretty good view, don't you think? And I think we will. Now I do have to apologize for the weather tonight. I ordered clear skies, and this is what we got. So I'm terribly sorry. You can fire me if you need to, but I figured if we had some really cool discussions to go on here, this one might be fun. Yeah. So I think that's a pretty good way to round out the evening. So it was sort of a bust with the meteors. It didn't really turn out too well. It's only getting worse here. I got to go out and close the dome before rain starts because it's going to be starting. You're talking about, and Daniel's asking me a question. So I think that we gave it our best shot, but this is not a year for the Perseids. It might be a year for the Leonids, though. And if we can see the Leonids eventually, then that'll be cool. The Leonids are well known for their huge numbers sometimes. Might be pretty cool. Yeah. You're firing whoever fires me? That's funny. Well, no. Look, like I said, if you want to hang out and talk for a while, I'm happy to answer some questions for you. And I know the sky's not too exciting, but what can I say? I'll bring up images of things to show you cool things, because now we've got way too many clouds to actually see any meteors right now through the clouds. It's too thick now. So I'm sad about that, but I'm not sad about that. I think it's okay. We'll be all right. So, it's pretty cool. And let me see if I can bring up something. Oh, this is just silly, but I'll just bring it up for the hell of it. This is an image that somebody did of me. Kind of a wacky astronomer image. It's kind of embarrassing, but I don't have a radio-controlled alien car. I want one though. Talking about things here, let's see. If you haven't seen Keith from P&K, I'm going to show you Keith. That's Keith. Oh, you want to see a bigger picture? Oh, all right. Yeah, this is Keith and I. And this is at Bill New York Skywatcher's house, where we actually were for the Pine Bush conference that we were there. I was speaking. Keith was there with Paul from P&K. So that was kind of cool. And this is not just a family album showtime. Believe me, I've just got a couple other things I was going to show you. Here's a neat one. This gives you something, but this tells you more about what I was talking about earlier. Okay, this is what's called the Big Bang timeline, and it tells you as when the Big Bang began, which is down here at the bottom. Okay, I know it looks crazy, but you look at the seconds here. We're talking about seconds to minutes to about here. Okay, and if you notice, in the very beginning there were no atoms. Okay, it was too hot for electrons to combine with protons to make any atoms, and of course the atoms that it did make when it finally made atoms were hydrogen. And what's interesting is in the era of synthesis, where protons and so forth, are created, and we start to see things combining. Were measured in just minutes in the early moments of the Big Bang. This document, if you look up Big Bang timeline, you'll be able to get this document or this image, and you can read, and it'll tell you all the interesting things here. Now, I deal with this stuff out here in the present, but you always have to be able to look back into the past to understand better what we're looking at. We had elementary particles, and we ended up. Oh, Daryl's going away. Okay, Daryl, we'll see you later. We'll see you. Have a good time. And Francis, good question. I do believe that there is more than one universe. Anyway, I'll tell you why. Big Bang timeline. Look it up. It's a great graphic. So, to answer your question, Daniel, I do believe that we do have a number of universes that were created, and it's not just me. There's a lot of people in academia that believe this now because of something I mentioned earlier, and that was that when we look at the nature of the universe, we see there wasn't enough mass to create the universe. That's where the concept of dark matter came from. Maybe there's dark matter out there. Fast radio bursts seem to confirm that, because fast radio bursts are changed as they come to us from these distant galaxies. They're changed by material between the galaxies, stuff we can't see. All right, so we see what dark matter does, but we don't necessarily have access to or see the dark matter. But when we actually look at the concept of our universe and the Big Bang, it appears that we may actually be one of several bangs, so to speak. Maybe ours is a smaller one, and there might be others that were spawned at the same time. And if that's the case, that would actually make for a very interesting universe indeed, wouldn't it? It's very possible that we're actually talking about a pretty cool universe if we actually can find that there's a way around that. And there's Oak Ridge, Tennessee. They're doing an experiment in one of the colliders down there, because neutrons have a very interesting capability, and this does have to deal with parallel universes somewhat. And I hope that Lee, the physicist down there, doesn't get mad at me for saying all this. But in the Oak Ridge experiment, it has to do with neutrons, and the deal is, neutrons, if they're left alone, a neutron all alone will spontaneously decay into a proton. Okay, and why is that? Well, because neutrons are made of 3 quarks. Okay, quarks have up and down. All right, and basically it just transfers. One quark just changes its up to down, and so forth, and you end up with a proton. So the bottom line is that this happens spontaneously, and there's a well-known number of seconds that it takes for a neutron to spontaneously decay to a proton. Well, they found that this specific time frame is different under certain conditions. When they're using neutrons, free neutrons that aren't connected to anything, and they're just stored in like let's, for the lack of a better term, put in a bottle and set on the side, they will decay in a certain amount of seconds, a number that's pretty exact. And if neutrons, free neutrons, are also the same kind of neutron, same exact neutron, are used in a super collider, it takes them a second longer to decay. And during that time, they seem to disappear, and then they're back. So, where do they go? Where do the neutrons go? Well, where the neutrons seem to go is what Lee and other physicists are calling a sector, and that sector isn't necessarily a parallel universe, but it is something that is different from what we understand now. And it's not quantum entanglement, okay? I'm coming to that, okay? It's not quantum entanglement, but it is. The neutron goes into a sector, a different place, where it's not visible to what we understand. We can't see it there, and then it pops back, and then it's visible again. So her experiment is going to be confirming that this is happening, and if it is, then we're going to have a whole new behavior of neutrons to understand. What's causing the delay? What's making it take longer to decay? I mean, that decay time is fundamental to quantum mechanics. That decay time is something that we absolutely depend on. So if it's going to change, that can cause serious problems. I just saw a bat fly in front of the camera. You'll see it in a bit, I think. Well, anyway, the change of the neutrons, that's something that is kind of like new science. Never seen it before, you know? So you mentioned quantum entanglement. Well, what's that? Quantum entanglement is something that, yes, spooky action at a distance. I like saying that. It's been characterized as that. And why do we call it spooky action at a distance? Because we don't really understand it. Let's be clear. Let's take a substance A. Actually, let's take this meteorite, which I have in my hands, which you cannot see because the lights in here just went off. If we take this meteorite and we split it in half, and we take the iron atoms, and we put half of them in laboratory A, half of them in laboratory B, and we change the characteristics of the atoms in laboratory A's iron, then we've changed laboratory A's iron. We haven't changed laboratory B's. Laboratory B's sitting over there by itself. So tell me why laboratory B's characteristics of its atoms change identically at the same time. See, that's quantum entanglement. They're still entangled. They're still communicating somehow. Isn't that cool? Somehow. We don't know what. We're scared. We don't know. But we do know that excuse me. We do know that it happens. And I have another theory, by the way. My theory is, and I've talked to people about this, if we think about people that claim to have clairvoyance, ESP, all these things to be able to see the future, whatever. Let me ask you a question. You're sitting at home. It's a Sunday afternoon, and you think of that friend you haven't talked to in 10 years, and they call you. Has that happened to you? Almost every hand in the chat will go up, I'm sure. The reason it happens to you, I think, is because of this spooky action at a distance. We actually, as organic beings in this universe where quantum entanglement occurs, I think we are subject to it as well. But I think it happens, and I have a funny word for it. I call it the brainular level. At the level of the brain, the brains are all made of the same material, right? have the same types of cells, the same type of neurons in every single brain. So maybe we are all entangled with each other. How about that? How about that? And so naturally, if we have this quantum entanglement between ourselves, then maybe we're talking about a fundamental property of the human race, which makes us very, very exciting to other races in the universe, which is probably why we could very well be visited by so many of them. We had flying saucers for a while, then we had triangles now. We've got all kinds of reports of aliens that have visited us. Are they all true? Probably not. But you know what? Only one report has to be real, doesn't it? And that's the answer, is they're here. And I do believe that they're here. I think that's very, very possible. I really do. So anyway, I think that considering quantum entanglement for the brain and how that explains why we can think of someone and all of a sudden they call us, one or the other was communicating via this quantum entanglement. Believe it or not, I use quantum entanglement every day. When I think, when a friend of mine pops into my head, I will sometimes pick up the phone and just call him and say, "You were just thinking of me, weren't you?" "Oh my God, yes!" That's typically what I hear. So basically, what I'm doing is establishing an experimental basis for quantum entanglement within the brain, and you should do the same. Daisy and Zoe, how you doing? Yeah, like twins that communicate from a distance. Exactly so. They're even more identical, and people say that twins can do that, and you're absolutely right. Thank you for mentioning that, Daisy. Or Zoe. I'm not sure who you are, which one you are. But I just wanted to tell you that you're absolutely right. And Daniel, yes, maybe it's dimensional. I mean, within string theory, we can have up to 10 different dimensions. Now, we only know X, Y, and Z are 3 dimensions that are all moving through time. So that gives us kind of 4 dimensions, doesn't it? Because time is sort of a dimension in a sense. So the bottom line is, if you have our 4 dimensions, maybe there's another 6. Maybe there's another 6 beyond, and that's pretty cool. That's pretty cool. Oh, I love the Blue Dandy Waltz, by the way. The reason is because I don't think of people dancing in these big flowy dresses and suits or whatever. I think of the Pan Am Clipper that's rotating and docking with the space station in 2001: The Space Odyssey. I work with, of course, Doug Trumbull, who is the visual effects wizard who did the special effects for Close Encounters, Blade Runner, and, of course, Stanley Kubrick's 2001. And we've been good friends for a number of years now, and Doug's responsible for what you see on the screen and accomplishing all the visual effects that you see. Very, very cool stuff, So, yeah. Yeah, actually, you're right, Francis. Einstein actually denied his own findings in some cases, which was kind of funny. But with that image of the black hole we saw earlier, that exactly proved Einstein correct, because the shape of what we saw was exactly predicted by relativity. Exactly that shape, with the glow on one side and not on the other, but a donut. Yep. I have to say, I was Astro Live. I was actually, you're right. Mass Effect uses quantum entanglement as well. Why not? It's out there. So I love that game too. So much so actually that on my music on my phone, I actually have some of the songs from Mass Effect. Call me a nerd, call me a geek. Okay, I accept. And you're right. But the way I met Doug Trumbull was really interesting. I was doing an NPR show on the X-Files for Connecticut, And the host told me, "Oh, I got to get you on with Doug Trumbull next time." And I'm like, "What?" And I was like nervous because, wow, that's my idol. The guy's my idol in all his movies. And he said, "Yeah, he's a UFO hunter just like you." I went, that's crazy. I went home and I wrote him an email. Didn't expect to hear from him. You know how you are. How it is. You write someone that's your idol and you'll never hear from them. Well, about a half hour later, I get a 1.5 page email back from Doug. And I was like, wow. So next thing I know, I'm standing in front of Doug and we're working on commercials because he saw my website, which is a visual effects website, just like his, just like him. And brought me up there to work with him and do stuff. And it's been wonderful. So bottom line is that you never know where life takes you, right? But yes, going back to Mass Effect, I love the sound effects and the soundtrack rather from Mass Effect. It's a really, really good game. You know another one that I really liked, and I'm sure you're gonna like this, Homeworld. And I have to admit, when I finished the Homeworld game and the credits start, I let the song play to completion. I just stared at the screen. I felt like I was watching a movie, and I felt like I was part of it. It was really so well done. So you tell me if you think Homeworld is also good that way. I like listening to the soundtrack very much, especially at the end. So, all right, well, I've been seemingly talking a lot here tonight. Well, what do you want? There's not much to see, right? So I'm sorry about that. But I do want to just thank you guys for coming out. It was a good attempt. We didn't get very far. My apologies. I wish it could have been a little better. But I will talk to you soon. I don't think I'll stream until I come back from Norway, unless I can get good Wi-Fi over there and I can do a stream. Because I'd love to show you some of what I'm doing over there. It'll be kind of cool. Anyway, thank you guys for coming out. It was great to see you. Thanks for hanging with me tonight. I know that we're approaching the end of this stream, but there's a lot of other Perseids streams you can go check out, which are still active, I'm sure. There's clear skies somewhere, folks. So you guys have a good night, all right? And I will talk to you on the backside. See you later.